绍一下。那下一位讲者是叶志宽，然后他在大学的时候是在宣田实验室做专题研究，然后那时候做的题目是用 reinforcement learning 去学习要怎么在潮牌里面玩那个 bidding， 然后现在志宽在 CMU， 然后跟 Pradi 在做关于解释性模型这方面的研究，然后那我们就欢迎志宽。
感谢。OK， 大家不介意我练习一下英文吧？就怕讲得太破。So, hi everyone. My name is Chih-Kuan Yeh. Today I'm going to be presenting understanding and interpreting machine learning models. This is maybe today I'm going to be talking about the background of some integral machine learning models, context, and also I'll be presenting one of my works in CMU, so which is representative point selection for explaining deep neural networks. So let's talk about some backgrounds on integral machine learning. So first of all, integral machine learning has been a growing area. Just look at the papers submitted in over the years. So it is growing at a linear speed. So why do people care about integral models? So there are lots of reasons. I will try to motivate some of the reasons why we need integral models. So let's talk about self-driving cars, or even robots that might dominate in the future. Like, are they safe? Or if we don't understand how they work, then how do we know it is safe to trust them? So a similar reason is like, how do we enhance trust? So this is a 2016 KDD paper talking about a binary classifier on an AI to predict. So basically, the AI is predicting whether this human is do they believe in God or not. So you can see that algorithm 1 and algorithm 2 produces the same prediction. However, algorithm 1 uses a feature such as God and stuff, while the algorithm 2 shows irrelevant features. So although they have the exact same training and testing accuracy, people might prefer algorithm 1. So this is how integral models might help you to apply machine learning models in real-world applications. Moreover, can we learn from an AI? So there are certain fields where AI has better performance than human, such as Go. And so if we can interpret how the AI does its model, can we use it to teach ourselves to become a better Go player? Or any fields where AI has a better performance than human? Moreover, how can we improve my model performance? So we know so this is a meme I saw online, where like in the statistical learning, people talk about BT dimensions, how to regularize my model to have better performance. And now in the more deep learning generations, people talk about stacking more layers. So like, if we can integrate our models, then maybe we can get more insights rather than training a deeper, more powerful neural network. And then there are still lots of reasons. And this is the last one I listed. I feel this is somewhat important. So if we learn from data, then the data might be biased. So a lot of people bias might be embedded into the data. So if we can interpret our model, we can understand if our model is biased. And maybe we can make unbiased our network or model. So there are still lots of reasons why we should think about integral methods. I just listed some out of my mind, and so I believe there are still tons of reasons why integral models are important. So for me, the general goal is to connect machine learning models to human understandable concepts. So people argue that some machine learning models are too complicated for human to understand at all. which is kind of true. However, there are some high-level concepts of machinery models which I believe can relate to what human can understand. So for me, doing an interpretive model is not about understanding the whole model prediction itself, because it is definitely too complicated for human to understand it as a whole. However, I believe connecting machinery models to human understandable concepts is possible. Also, if we can make this connection, the goal is to enhance the human trust machinery model and also improve the model performance by human knowledge. So there are different types of interpretive methods. So like before building any model, you can look at the data and see if any model is trained based on these data, what thing I can learn from. You can build a completely understandable interpretable model, or after building a model, you can like download any TensorFlow weights online and then try to interpret this model I download online. So there are like 3 different places where you apply your interpretive methods. So, I actually haven't finished. I haven't finished the slides here. So, I'm trying to introduce some of the common methods on interpretive deep models. But for now, I only show the silencing features. So, for example, so this is something I kind of question, but this is what many people commonly think what interpretive deep models is. So this is an image of a camera, and then some silencing method will show what are the most important features the deep neural network faced to make this prediction. So you can see on that. That is the image from integrated gradient. So the question is this a good enough explanation? And so if the deep neural model makes prediction on these features, can we trust the model? However, I'm not going to talk deep into this in this presentation. So let's show another paper, which is why should I trust you? So basically, for this original image, they show the partial features that predicts electric guitar, acoustic guitar, and laptop. So, so if you're given these explanations, will you be satisfied? So this is the so there are still other methods on interpreting deep models. So I think the more mainstream ones are showing important training examples, and also maybe mainly the second one here, which is you approximate complicated models by more commonly believed self-explainable models. For example, linear regression, rule-based model, decision trees. Like these models are more thought of human understandable. However, it is too complicated. I still doubt if you can understand it. Okay, so now I hope everyone kind of believes that interpreting machinery models is important. So now I'm going to present my work, representative point selection for explaining deep neural networks. So high level, we enhance the understanding of the neural network by showing a set of training examples regarding the whole network or regarding a prediction. So for example, so this is an image of a grizzly bear. So we actually show that the prediction of grizzly bear is made by influenced by these positive examples and these negative examples. So actually there are a long list of positive examples and a long list of negative examples, but we show the most important ones. So later I will tell how we can motivate this, like what are positive ones, what are negative ones, and how can we define their values. Okay. So in fact, we can actually show that. So given a deep neural network, let's call it F. So the prediction of this image can be actually shown as a linear combination of some kernel function. Just think of it as some function that measures the similarity between the testing image and this training image with some positive coefficient, and then summation all the positive images, and then also summation over all the negative examples. So what does this mean? This means that there are a set of given positive and negative training images in the training data. So if this testing image is closer to the positive training images and farther away from the negative training images, then prediction is higher. If the testing image is closer to a negative training image and further from the positive training image, the prediction is lower. So actually, let's go back to this image. So we can actually see that the negative images are actually belongs to a class of polar bear, beaver, and pig. However, visually, I believe they all kind of look like this grizzly bear. And the first positive row examples mainly consist of positive examples. So, so basically we give another interpretal understanding that this is what the deep neural network actually does. It actually does kind of a weighted k-nearest neighbor. So whenever it is closer to pre-learned negative examples, then it will learn to decrease the prediction weight for grizzly bear. However, if it is more similar by visual feature to the positive examples, then the prediction weight of grizzly bear will increase. Okay. So we have a more formal theory statement, but I'm going to skip this slide because no one is going to want to read this. So okay, let's also skip this slide. Okay, so basically, how do we prove that? So basically, it is simple. Let me explain it this side. So basically, we can think of SEM. So basically, for deep neural networks, for like this. So this is a black box where we don't care what it is. It can be any network we design, like convolution, recurrent network, anything. We think of it as a black box. So our only constraint on the deep neural network is that before activation, there is a fully connected layers, which for all the classifications models I know, this is true. So basically, we think of this place as a black box, and then we just think of it as feature extraction. So basically, high level, we just think of this network as a linear layer, and we just consider the last layer. So basically, how we do this is actually similar to SVM. So if we think about the dual form of SVM, it actually can be written as a linear combination of training instances, where the non-zero weights are actually called supported type, I believe. So basically, if we think it in that way, and then so we solve an optimization that contains everything, but also contains the last fully connected weights. And then basically, our theorem basically shows that if you add L2, small L2 weight, so actually the L2 weight just needs to have any non-zero positive, just any positive weight for the L2 regularization. And then if you solve it to stationary point. So a point to note that is for usual deep neural networks, you basically use HGD, so you will not get that close to stationary point. However, if you just use gradient descent with line search, you can easily converge to a stationary point because the L2 regularization is just imposed on the last fully connected layers. So after you solve this objective function, so after you solve it to stationary point, you can just take the gradient to be 0, and then you will simply see that the weight of the last fully connected layer can be written by a linear combination of training point features. So this is this is straightforward because when training, you have training loss of all training instances with an L2 regularization. So if it is solved to stationary point and you take the gradient, the L2 regularization gradient becomes the weight and everything else is linearly separable. So basically, you can decompose the fully connected weight for a term that is a linear combination of all the training point features. So after you do this, the testing point is actually just the linear product of the weight and the testing point feature. So basically, if you do this linear combination, you'll get that the prediction of the testing point is just a linear combination of the product between training point feature and testing point feature. So this is just a very high level idea of a proof. It's very simple. The proof is 2 line. If you want to see more, you can read our paper. So basically, this is what we do. So we decompose the last fully connected weight as a linear combination of all training data. Where here, the important thing to note is that for every training data, we will actually get a value alpha, which specifies the importance of this training data on this weight. And then if you make prediction on testing data, you'll get that the prediction of the test data is actually a linear combination of alpha I with a kernel function between the training data and testing data. Okay, so after seeing this form, let me give some more intuition about why this is important. So let's say if we have a testing data which has a high prediction function, then what does this mean? So for that, normally we do not have much intuition about this. However, if we look at that form, for that form to be high, we know that 2 things. So because the summation is high, then there must be some terms that have high value. And for any term to have high value, 2 things must satisfy. First thing is the kernel function between training data and testing data should be high, and also the alpha I importance value should be high. So for the kernel function to be high, and also our kernel form is just the feature product. So for the feature product, for a testing point and training point to be high, usually that means that the testing point and training point should look similar. And for the alpha I to be large, this basically means that this training example should be marked as an important training point by when we learn the neural network. So because this is a linear combination, we can actually decompose every training data point's importance value on the testing point's prediction. So this alpha I kernel function between xi and xt, we call it the representative value for a training instance xi on a testing point xt. Okay, so yeah. So this basically brings us back to what I said in the first point of slide. So basically, if the testing point is closer to the training point, it has a larger prediction value. If the training point is closer to a negative example, then the prediction will be lowered. So basically, what I said before, there are two cases. So first, if you have a freedom of training a neural network, you can just directly solve for whatever ERM you have, and then just add a LT regression on the last one connected weight, and then solve it to stationary point. Then directly, you can get a closed-form solution of the representative values, and you can use the representative values. I will show how they are useful in the later slides. So the second problem is that, let's say if I downloaded some weights online, and it is not trained in this form, then how do I get this representative value form? So the solution is actually simple. We can just define the loss on the original network and our new network. So basically, we train a new network that is constrained to have a close prediction to the original network, and then we just add L2 regularization. So for any lambda is larger than 0, if this thing is solved to global any stationary point, then we can also decompose it for our representative values. And we know that for ReLU and also softmax, activations, we can actually design a loss to be convex. So this whole thing is strongly convex, and you can easily be solved to very close to global optima. Also, lambda can be arbitrarily small. So in theory, you can find a point that is very close to the original prediction, which is you can find a network which has almost the same prediction as the original network, and also it can be decomposed by representative values. So let me show some of the experiments we do to demonstrate that the representative values are actually useful in practice. So we did an experiment where we randomly corrupt 40% of the data on a CyPAR 10 dataset. And then, so our goal is to try to identify which training points that is most important, that we should try to inspect them and fix their labels first. So we can actually directly use the alpha that we learned, the alpha values that we learned from representative value, and inspect those training points with the highest alpha. So we can actually see that our performance is better in terms of the testing accuracy recovery compared to the influence function. So influence function is basically this is ICML 2017 best paper. Basically, it's talking about how if you remove a training point, how will this affect a testing point's loss. So yeah, so this is our first experiment. So our second experiment is on misclassified examples. So here we want to learn why our deep neural network makes an incorrect prediction. So first we see this testing image where it is actually an antelope, but it's predicted as a deer. I don't know if you can see this, but basically this is a misprediction. So we want to understand why does it not predict it as an antelope. So we actually look at the negative examples for antelope prediction. And then so we see 4 images throughout all misclassified antelope predictions. And then this is what we find. So we find many training images where there is actually an antelope in an image, but that is because there is also another animal. It is predicted as zebra. So we actually find that because this image looks like this image, and this image is a negative point for antelope because apparently the model tells it to not predict as an antelope. So the prediction of antelope for this testing image is suppressed, and it leads to higher training error. So this gives up some intuition. How do we improve our training process? If we remove this noise in their training data, or maybe we add like multi-label classifications, maybe our prediction will be better. So here we so this is the form that I showed on the first slide. So if we take partial derivative on the image on both sides, we can actually get the gradient on the left-hand side. And basically we know that gradient is one of the main component of all the saliency maps, many of the saliency maps method. So basically the gradient itself can be seen as a saliency map. And there are lots of saliency maps that does linear operations on the gradient saliency. So because we can do, we have this linear we have this linear form. So then we can decompose the saliency map onto the contribution of each training images. So here we actually see that. So in this image, the first column is the testing image and its saliency. And the 4 images are the top 4 positive influential training images. And then, so basically what this means is that the saliency map of the testing image is the so the sum of the 4 saliency map plus, so the sum of all the saliency maps in this row will add up to this ANC map. So what intuition can we learn? So in this image, I'm not sure if you can see, but basically there's a small animal there, and so the sensing map mainly focuses on the animal here, and also the background here. So if we look at the contribution for each training image, we will find that when the animal is larger, then the sensing map mainly focuses on the animal here. However, there is some training image where the animal is very small, but it has a greenish background, same as the testing image. So in that case, the tendency map will focus on the background. So then you take a summation over, and you can see why the tendency maps focus on both the animal and the background. Also, in the zebra case, we can see that the zebra's head is focused here. And then when there is a very large zebra in the training image, the sensing map will focus on around the zebra's head more. In other cases, it will focus some on the head and some on the background. So it gives us a deeper understanding on how sensing map works. So lastly, we also have the benefit of a faster computation efficiency. So as I mentioned, the intel function, which is a ICML 2017 paper, it basically uses a Hessian gradient product on the testing image and the training image. So basically, because of the Hessian calculation, the computation cost is high. Even they do a lot of approximations to speed up their computation. For one testing image, and you compute the importance for all training examples, our computation is around 1,000 times, like 3 orders faster than an inference function. However, our method requires a fine-tuning step, which the inference function does not need. But as we can see, like just computing the computation for one testing image, the inference function has a higher cost by our combination of the fine-tuning and our real-time prediction. So basically, also the fine-tuning is just a one-time cost. So our method can be used in real-time application where it might be difficult for the inference function. Okay, so in conclusion, we enhanced the understanding of deep neural networks by pointing out some important training examples. Our method can be used as itself as an integral model or also a post-hoc explanation, and our method is efficient. Okay, thank you, everyone. Are there any questions? Some of the 就是比如说刚刚的 sensitivity map 可能是一个 potential 的 solution， 就是比如说你可以看出，比如说你可以看说这两个会很好，然后你可以看，你可以用最聪明的开始，你做三分之一，基本上是那个 NLP 的三分之一跟 word 做三分之一，然后看是哪些 word 指的这个开始跟推理的 example， 会让他们的应该率很高，你可以用。我believe general 就是一个 open hard， 但是对于目前来说比较没有问题，因为一般都是 word， 就你主要做的
如果跟那个 distance function 有点话，
这个方向应该是说，就是对每个 training point， 它会算那个海选跟 training point 跟开心 point 的 gradient 的数，就是它应该没有符号什么的，
他们有选练高法。
对，它应该是说，你给我一个开心 point 跟 training point，就可以直接算说，假设我把这 training point 拿掉，我的开心 point 到 training point 多少，然后就直接用一个海选 gradient 就 gradient 海选。就是这个秘密就是对于这个 model 来说，这个training point 分数有多少，在这个经验很明显的用分数有多少，然后呢，流上越大就表示这个 training point 对这个结束是怎么样。
你有看到某种情况是，比如说它的 alpha 跟 Yu-Sheng，但它是
会啊，但是这样的话就不会可以得到 prediction 因为其实 similarity 的，至少在 image value 来说 ，similarity 的分数不会差太多。然后呢，所以 alpha value 会有点高。但是我觉得如果是 NLP 的话，可能不一样。NLP 的话，就是 similarity 的差距很大，有时候正有时候负，然后就会比较 human 比较没有办法受不了。
是在变，是把，是你用特别多建一个 layer 去专门去设定的好法，是你在跑遍 SGD 的时候，同时就会得到那些好法。
对，就是你可以看，就是这个 formal theory 这个里面，就是你受到这些会的时候，它把你分上去。
哦，可是你是说你，可是基本上你不会找到这些。
所以就是我觉得来这边就有个抓到什么的，你像过去你就是说，我 fine tune 这个 final 那个 final version 的，中间多对新的，我觉得 final 它 existing 的，我可能有把 fine tune 到这些。然后呢，我的可能说 fine tune 这些课以后，这个新的题目可能就不会好好。然后呢，到这部分以后就不会。
之所以要是直接从零开始劝的话，
就是还是要确认身份，就是你的第二。